do the evaluation or like trying to conform to the way of evaluation. And one of them is that you understand the objective of everyday lessons. And because if I came in and asked you what we were learning about today, that you'd be able to tell. This is in every section of your book. It says in the first page of the section, it says what you're going to learn about, and it says why you're going to learn about it. Today we're going to talk about velocity again, which we talked about already when we talked about the first instantaneous rate of change. We talked about derivatives. But today, since we know the shortcuts, we can look at that a new way. And we're also going to talk about a little bit more than just velocity. We're going to talk about acceleration, and we're going to talk about how do they connect to what we know about derivatives. And the reason that's important is because anytime you're talking about the rate at something is changing, if it's a straight line, you're just talking about slope. But most of the things in the world do not work out to be straight lines. And so when you talk about how fast is the price of gas changing, or how fast is anything changing, you can talk about derivatives. And so that's a real life application of derivatives. And we're going to see that when we see story problems. Talk about draining a tank, and the rate that the tank is draining can be related to a derivative problem. So that's where we're going eventually. You're not writing this down, right, Neil? You're not writing like what you learned about? This is just for you. You could just like, this is really all you should have written down, right? You good? Okay. You're writing a lot. I was very excited. You should write this. We've talked about the difference between the average rate of change and the instantaneous rate of change. If you want to find the rate at which something is changing at a specific point, you can do that whole limit of a plus h, right? You're getting closer and closer to that exact point. Well, we know that's the derivative now. So another definition of instantaneous rate of change is just the derivative. And so it's been a few days since we've talked about the limit definition of a derivative, but remember that this is how you find a derivative. You take the limit as h approaches 0. H is that value that gives you the secant line. And as h gets smaller and smaller and smaller, this becomes the tangent line, or it becomes the instantaneous rate of change. So just know that the derivative is the same as that. So now that we know all these shortcuts, like the power rule and the quotient rule and product rule, we can do this a lot easier, a lot less work, which means we can also deal with a lot more complex functions. And the book says when they say rate of change, they mean instantaneous rate of change. The only time that you would be doing the average rate of change is if it says the word average there. So I wanted to put that on here because that's kind of the way the book talks about this. If it says find the average rate of change, that's just given 2 points, you can do the slope, and you say how much is changing, what's the distance over the time. And so some of these problems are kind of long. That's bad, right? I think I might have taken some of these from your book, but we can write it down a little bit. This one I didn't.
Wait, where did you say the average rate?
Remember we did that, chapter 2.
Wait, what's it? It's not the same thing as instantaneous.
No, average rate of change is given 2 points, average rate of change over the interval from A to B. It's like saying if I drove, started at 0 miles and I drove 100 miles and it took me 3 hours, what was my average rate of change or my average speed? You take the total distance divided by the total time. Or average rate of change is FB minus FA over B minus A. Slope.
What's under the limit if I have the limit gets to that?
H approaches 0. So let's look at some problems today that are not just, say, find the derivative. They're like story problems. Oh my gosh, all this is still here. Don't look. Oh my gosh. I really had lots of trouble with these notes today. I swear I saved them like 4 times and then I could never find them.
Physics and just as well.
What?
Oh my god.
Like I did them yesterday, and then in 7th hour I went back to change something, and I couldn't find them, so I opened them again and erased everything. Saved them again, and then this morning I went to open them and it wasn't there, so I opened it again, but I didn't erase everything because I thought it was already erased from yesterday. Alright, so these problems aren't that hard, it's just understanding what they're asking. And again, that's a big part of doing calculus, is being able to take what they're asking and change it to an equation or do the problem. And so this one says a square of side length S is inscribed in a circle of radius R. Write the area of the square as a function of the radius R of the circle. What does it mean to be a square inscribed in a circle?
Like, it's a square inside the circle, and like, make a square inside.
Yeah. Inscribed means that the square is inside the circle. If it said the square was circumscribed in the circle, that means it was the outside of the circle. So I think I can draw a picture here. So here's my circle, and here's my square. If it's inscribed, that means all four corners of the square touch the circle.
What do you call it? It's not touching the side.
It's just in it, it's not inscribed. If it's circumscribed, the square's on the outside, and the circle touches the square in four corners. No, circumscribed. You just have supersonic hearing, just so
I
you
feel
know.
like
I hear a lot of things.
I probably don't want to.
Yes, and I ignore many of them. And pretend I don't hear them. And then I go and tell Miss Hodge. Alright, so the side of the square is S. So I could say this is S, and this is S, and this is S, and this is S. And the radius of the circle is R. And we're trying to relate the area of the square to the radius of the circle. Half of S would equal your radius. Do you agree with that?
Could it be a rectangle or does it have to be a square?
It has to be a square. What if I drew the radius in like this? From here to the corner, would that be a radius?
Is that who we're using triangle?
And if I do another radius from here to here, would that be a radius? Could I write an equation relating R and S using that lovely little picture I just drew?
R squared plus I squared equals S squared.
Yeah, this makes a right triangle now. So I could say that R squared plus R squared equals S squared using our favorite theorem, Pythagorean theorem.
I use that in real life. Years ago.
So that would be 2R squared equals S squared. Let's go back to what we're actually trying to do, because we're kind of, sometimes I get lose focus here. We're trying to write the area of the square. Well, how would we write the area of the square in terms of the side of the square? Forget about R for a minute. How do you write the area of a square? Yeah, could I say the area of a square is side times side, or S squared? Do you agree with that? If it just said write the area of the square, we could be done. But it says write the area of a square as a function of the radius, which means they don't want S in here, they want R in here. So I went back to this because we could actually solve this for S and take the square root of both sides. Do I need to? If S squared equals 2R squared, can I just replace S squared with 2R squared? And so I think write the area as a function of the radius would be 2 times the radius squared would give me the area of that square. That wasn't really any calculus at all, right? That was some good old geometry. Now let's throw some calculus in there. you that means instantaneous rate of change of the area with respect to the radius r of the circle. Notice they're not giving you a value. You're not going to get a number here. You're just going to get an equation. But when you see instantaneous rate of change, what does that tell you that we're going to do? What did we just write out on the previous slide? What is the instantaneous rate of change equal to? Yeah, the derivative. We don't need to do the limit way anymore. We just need to find the derivative of that function. We just use the power rule. Instead of y and x, we have a and r. Normally, we can say dy over dx. In this one, I could say dA over dr. I'm finding the derivative of a with respect to r. That's why it looks like that. And what would the derivative of that be? 4r. What this represents is the rate of change of the radius. The rate of change of the area with respect to the radius. So now that we found the rate of change for the area with respect to the radius, it says evaluate the rate of change of A when r equals 1 and r equals 8. Yeah, you just plug it in. So when r equals 1, the rate of change of the area, dA over dr, is just going to be 4 times 1, which would just be 4. That's pretty easy, right? And when r equals 8, we would get 4 times 8, or 32. Again, notice it says the rate of change, so that's how you know to plug it into the derivative. If it said find the actual area, you'd plug it into the area formula. So it's really important that you're reading these. One more. This is like a free response question, Caitlin, because it's like a never-ending question. That's what a free response question is. It's like 3 or 4 parts, only way worse than this. The other, okay, sorry. I don't know what that means, but no. We have free response questions. 6 free response questions. 47 multiple choice. That's the AP test. About 4 hours. The other thing that we care about when we're talking about real life problems with rate of change is the units. And a lot of times on the free response question, 1 point of the 9 points that each of those questions are worth would be putting the correct units on a problem with the rate of change. So it says, if r is measured in inches and a is measured in square inches, which makes sense. If this is your radius, when you find the area, it's going to be square inches. What would be the appropriate units for dA over dr? And really, it's not a trick to do the units. What are the units of the area?
Square.
And what are the units of the radius? So we could say the area is changing with respect to the radius in inches squared per inch. Seems kind of weird because they're both in inches. We can kind of simplify that, right? Inches squared over inches would just be inches. Lots of times the units aren't going to be the same. Like the top value might be in, I don't know, feet, and then the bottom value might be in time. So it'd be like, think about velocity in feet per second. And so it's not a trick when you're doing that. You just want to think about what were the units of this, what were the units of this, and put them over each other. And so again, that's an important part as we're going in there. So the first part of your homework today has a little geometry in it, kind of like this. And we'll see if you need to know any geometry formulas. So I need to tell you. Here's the other important thing for today. my gosh, don't look. Again. This is top secret. Okay, remind me before I go to the next slide. That's just erase stuff. I could write it all down. Here you go with answers. This lovely equation at the top is the equation of a position function on anywhere, really. It's kind of a really ugly, it looks really scary. Most of the time, these problems in calculus, they're going to give you the position function, like they're going to tell you what it is so you don't actually have to figure it out. But you could. And I kind of wrote this down here, but G, I believe, is like whatever gravity has to do with, like, on Earth, we always plug in -16 for like -16 feet per second or something like that, right? Some of you physics people tell me that I know what I'm talking about. And in meters, it's like -32, like you.
Say 16 squared.
Right, like this is 16, so I guess maybe we plug in 32, but then we take half of it. Is that the acceleration due to gravity?
9.8.
That's meters, but what is it in feet? Yeah. So anyway, the G is like gravity, T is your time in seconds. V sub 0 is your initial velocity. We did this last year in pre-cal a lot. So how fast it's going to begin with. And S sub 0 is your initial height. Like I said, most of the problems we do, they're going to give you that equation, so you don't have to plug all that stuff in. But you could. And in your book, they actually give you those two equations without G. Like they plug in 9.8 meters per second, or I believe it's like 32, and then half of it's 16. I don't know. Anyway, it's in your book. But we're going to call that first function the position function because it tells you how high that object is over a specific time. If you like throw an object in the air or launch a rocket in the air. That's what that does. Here's the new stuff that we can say. If you take the derivative of the position function, you will always get the velocity function. So the derivative of the position function will give you the velocity function. So if you want to know the velocity or how fast that's going at a certain time, you can just take the derivative and plug in whatever time that is, and you will get the velocity. And so S prime of t is the same as the velocity at t. So those are equal to each other. And then guess what? If we take the derivative again, which we could either write that as the second derivative of the position function or just the derivative of the velocity function, that will give you the acceleration function. And so again, we can write that lots of ways. We can say that's the second derivative of the position function, or it's the derivative of the velocity function, or that's the same as just saying the acceleration function. So again, I feel like calculus is a whole lot of notation and knowing that all of those mean the same thing. And then we also throw in speed sometimes. Speed is almost the same as which one of those? Position, velocity, or acceleration? Velocity. What's the difference between speed and velocity? Yeah, velocity has direction. So if something's falling, velocity is going to be negative. Speed is always positive because speed is the absolute value of velocity. So I'm just going to throw in here that if you want to find speed, you just take the absolute value of the derivative of the position function, which would be the same as taking the absolute value of the velocity function. Yeah. Their absolute value. Speed is always positive. If velocity is negative, that just means the object is going down, it's falling. All right, so let's see if we can get through a problem. A really, really big problem. everyone goes me going, this is a really important thing, so make sure you have this written down. Don't look at this. Just here. Oh, this is a lot. Write this down. It says number 13 on page 136 in your book. And honestly, for your notes, you really just need the numbers out of this. And so a rock is thrown vertically upward from the surface of the moon, which means the gravity is different on the surface of the moon. But you need to say the velocity of 24 meters per second. So you put like a rock is thrown, velocity 24 meters per second. And it gives you that starting function. It says it reaches a height of s equals 24t minus 0.8t squared meters in t seconds. That means if I said how high was the rock after 4 seconds, you could just plug 4 into that problem, and it would give you the height. That's what the position function does. What we're going to do is answer a whole bunch of questions about this. And so there are parts A, B, C, D, and E. So I really want you to write the parts down for sure. I used to have this button that would let me do like 2 pages so you could still see this page and the other page. Remember that button? How come I don't have that button anymore? I just moved this to the bottom. Just gonna make it big, isn't it? Oh, Andrew, you're a genius. Oh my gosh. Hit it. Hit it. Okay. It's really small now, but. Find the rock's velocity and acceleration functions. So, my S of t is 24t minus 0.8t squared. And if I want to find the velocity function, what do? Take the derivative of this function. So to find the velocity, all I'm doing is taking the derivative of the position function. That's the definition of velocity in terms of calculus. It makes things really nice when you're trying to figure velocity. And notice this isn't that bad of a problem. We could have even done this with our limit definition, but it's much easier now that we don't have to do the limit definition. What's the derivative of 24t? Minus, I have to pull the 2 down, so 2 times 0.8, 1.6, I think. 1.6, and then subtract 1, so we get t.
Say outside of class, I have a physics test.
If they give you the position function, yes. And just throwing out here, this was in meters, and t represented seconds. So another way of writing this is we could say we're finding ds, oh, we were saying ds. We could say ds over dt, where s is my y and t is my x value. What is the units on s right now? Meters, and time is in, so the units on your velocity are meters per second. When we're talking about throwing an object in so many seconds, yes, it's always going to be time. On the last one, it wasn't in time because we were talking about the radius and the area. So.
We have 2 different things where it won't be seconds.
Oh, right. Time should always be on the bottom. Oh, wait, I'm not done. I'm not ready for B yet. What else was I supposed to do? Find my acceleration? My acceleration function is what? How do I find acceleration? I don't want the answer, but. the derivative of the velocity function. So it's going to be the derivative of the velocity function and this is just going to be 0, and this is just going to be minus 1.6. Do you agree with that? Which means this is a constant function. The acceleration is staying the same the whole time. What would the units on this be? We're doing this with respect to time again, right? So it's like taking dv over dt. And what were the units on the velocity function? Meters per second over seconds. It's going to be meters per second squared. Acceleration is always in per second squared. I'm not a big physics person, so I can't really explain to you what that means, meters per second squared, but I can tell you that it's always seconds squared when you do acceleration. Part A. 72. I told you already, but you weren't listening. I really need like an extra period of calculus. I have so many more notes today. Lots more. How long did it take the rock to reach its highest point? There's lots of ways we can do this. We did this in pre-calculus last year. It was a whole lot of algebra work. What kind of shape am I going to get if I throw something up in the air? A parabola. Do you agree with that? It would still be a parabola because it would still go up and have that moment where it stops and then come back down. So if I'm going to throw it up and it's going to look something like that, what am I looking for the highest point? The maximum. Now we could go back and we could look at the position function and we could try to find the maximum or graph it and find that. But let's think about what we know with calculus. What do we... Say that again? Where the derivative is 0. Do you remember when we talked about horizontal tangent lines? Do horizontal tangent lines occur at maximums and minimums? Which means instead of having to do a whole bunch of algebra or have to graph it, if you want to find the maximum or minimum, all you have to do is find where the derivative, or in which case, which one of these equations am I going to be using? The original, the velocity, the acceleration. Where the velocity equals 0. Do you agree if you throw something up, at that point where it turns, is that like the point where the velocity is 0 and then it starts falling back down? It's like that moment that on a roller coaster, I don't know if that's the same thing, but like that hovering moment where it's like stops for a second and then it turns back down. That's the velocity equaling 0. Horizontal tangent line, the slope's going to be 0 there. So all you have to do to part B is know what it's asking, and all you got to do is set 24 minus 1.6t equal to 0. And that's it. No graph needed. Calculus is amazing. It is amazing. You should go back and do this the long way, and then you'll think it's amazing. And I think if you divide that out, it works out to be 15. We're solving for time, so what would my units here be? 15 seconds. Not meters, because we're just solving for time. How long did it take? Which means, at what time did that occur? Well, a lot more, but we're at least doing part C. How high did the rock go?
Wait, so we have to find where it was when it was 0?
Plug 15 in where? Because we know it took 15 seconds for that to occur. Into the original equation because the original equation gives you height. So these do not take a whole lot of work. It just takes knowing which equation to plug it into. Oh, yeah, that was good. That was good. How high? We know that it took 15 seconds. So all we have to do is take 15 seconds and plug that into the position function. So I'm going to do S of 15, which is 24 times 15 minus 0.8 times 15 squared. And I think I get 180. And if I'm talking about the height, what would my units on that be? Meters. Okay, we're gonna just have to see what we can do on homework because I have way more stuff that we can do. Like I saw D&E. Maybe you should try to finish this for homework. This is part of your homework. See if you can figure out D&E. I know it's odd, so obviously you can look in the back book to get the answers, but I want to see if you can figure out what we could do using these equations to get those answers. And this is in your book, number 13, page 136, so you really don't have to write it all down if you don't want to, but it's a lot. Like in the air. Then let's see what homework we can do. All right, so can I go from this page? How do I make this go away now, Andrew? Is the real question. I don't see the page. We can definitely do 1 and 2. Let's try 9. All right, and then let's do 14 and 15. Let's just kind of hold off on that and let's explore this tomorrow. And try to finish that last example. See if you can figure out what to do there. And 1 and 2 are like our first example. 9 is a picture, and they're asking you about a particle moving, and we'll kind of talk about that one tomorrow too. But that's a good AP question, number 9. And then we'll finish the others. Go back and look at my problem.
Oh, yeah.
Right, if you know halfway. Isn't this exciting stuff?